In this video, we're going to talk about the spanning set theorem. So let's try to understand exactly what it is that we're learning here. We just learned about what a basis is. And a basis is essentially going to be an efficient spanning set containing no unnecessary vectors. The spanning set theorem is going to help us in that understanding. And the spanning set theorem says this: we have a set of vectors S that are in our vector space V, and H is the span of those vectors. If I have some element in S that is a linear combination of the other vectors in S, then if I take out this guy, that what's left over is still going to span H. So before we look at a proof or anything else, let's just make that make sense. And I have a super duper easy example, very elementary example for us to look at, because that, for me, is what helps it to make sense. So here's my set S, 1, 0, 0, 1, 0, 3. Let's call this guy V1. Let's call this guy V2. Let's call this guy V3. Well, looking at that, hopefully you can see immediately that this is not a linearly independent set of vectors. And I can see that because V3 is really just 3 times V2. Therefore, V3 is a linear combination of the remaining vectors in S. What the spanning set theorem tells me is that if I take this guy out, that what's left over still spans H. Well, in this case, 1, 0, 0, 1, H is obviously just R2, because 1, 0, 0, 1 span R2. And did I change anything by taking out V3? Can I still span R2 without the vector 0, 3? Of course I can. I've got 1, 0, 0, 1. It's the easiest. It's the base of all bases, if you can imagine that, for S2. It also tells us, the spanning set theorem also tells us that if, assuming that H is not the 0 vector, that there is some subset of S that is the basis for H. So what does that mean? Remember that a basis is linearly independent vectors that still span the same region. And that's what we're talking about here, is I'm saying if I take out this one vector, what's left over is still going to span the same region, and bonus, those are linearly independent and therefore form a basis for H. Great. So let's look at what that means in proof form. Let's say I've got some arbitrary value x that can be written as A1, V1, A2, V2, all the way up to A, P, VP. And that is in H. And why is it in H? Because again, H is the span of those vectors, which means anything in H can be written as a linear combination of the vectors in S. All right, let's let VP be my arbitrary vector that can be written as a linear combination of other vectors. So VP can be written as A1, V1 plus A2, V2, all the way up to A, P minus 1, V, P minus 1, which means X is actually A1, V1 plus A2, V2 plus all the way up to AP, and remember that's just our scalar, times VP, which is A1, V1, A2, V2, oops, all the way up to A, P minus 1, V, P minus 1. Where did I get that? I'm just substituting this value in for VP. That's all I'm doing. So what's the purpose of that? Why did I do that? Well, we've got this X that's in H, and that X can be written as a linear combination of everything excluding VP. Therefore, what have I just shown? That V1, V2, all the way up to VP minus 1 spans H, or equals span. Let me try that again. That span, all of that, excluding VP, still is H. So I've shown this to be true. And again, did I show it for just one example? No, I showed it for some arbitrary VP. So VP could be any of the vectors. Part 2 says, as long as H is not zero vector, then some subset of S is the basis for H. And I don't really have room to show a proof of that, but essentially what we would say is if we have X that belongs to H, and I'm able to then take out the arbitrary vectors and still end up with an element of H, and keep doing that and keep doing that until there's no extras. I take out all of the extras, and what's left over is still going to span, because we know, we just proved that part of it. And what else does it tell us? It tells us that we're essentially going to keep going until we get down to a set that is in fact linearly independent, like we did here when I took out just one vector. I can take out as many as I need to get down to that point, and what's left over is going to be linearly independent and span the subspace, and therefore is a basis. Let's look at an example together that's perhaps a little bit less abstract. I've got three vectors, v1, v2, v3, and H is the span of those three vectors. And also note that v3 can be written as a linear combination of v1 and v2 by taking 2v2 minus v1. I need to show first that span v1, v2, v3, also known as H, is equal to the span of v1, v2, and then find a basis for H. So there's a lot going on, but I feel that we can do this. Let's just remind ourselves, anything in span v1, v2, v3, what that tells us is we can write anything as c1, v1, c2, v2, plus c3, v3. That's anything in span H, essentially. Anything in H is going to be written in that format. And anything in span v1, v2 can be written as c1, v1, plus c2, v2. So the first thing we want to talk about is the fact that anything here is going to be in span v1, v2, v3. Well, how do I know that? Because this is c1, v1 plus c2, v2 plus 0, v3. So wouldn't it make sense that if I added 0 v3s, which makes it still in span v1, v2, that any of those items would belong in H? Sure. That doesn't prove that they're equal. That just proves that everything in span v1, v2 is actually in H. So now let's let X be some arbitrary vector in H. So keep in mind that X is the form c1, v1, c2, v2, c3, v3, because it's in H, which is the span of the three vectors. Since v3 can be written as a linear combination of the other two, then X is the same as c1, v1 plus c2, v2 plus c3 times 2v2 minus v1. Great. So what does that tell us? Do you like how sometimes I put the vector sign on top and sometimes I don't? Let's just take it off for clarity. So continuing down this path, I've got c1, v1 plus c2, v2 plus 2c3, v2 minus c3, v1. So I can rearrange and have c1 minus c3, v1. And then for v2, I've got c2 plus 2c3, v2. So what does that tell me? Well, that tells me that X belongs to span v1, v2. And we already knew that every vector in v1, v2 belonged to span v1, v2, v3. Therefore, because I've sort of proven it in both directions, that H, or span, I'm not even going to use H, I'm going to use span v1, v2 is the same as span v1, v2, v3. So check, check. Show that the spans are equal. True. Then it says find a basis for the subspace of H. Well, a basis, remember, is a linearly independent set that spans H. Well, I've already just shown that what I have, that v1, v2 span H, because it's the same thing. And if I take v3 out of the equation, what I have left are linearly independent values, and therefore v1, v2 is the basis of H. So the basis is v1, v2, linearly independent and spans H. Here's another example for us to look at together. I've got v1, v2, v3. H is the span of those three vectors, and also 4v1 plus v2 plus 3v3 is equal to 0. And I need to find three distinct bases for H. So let's talk about how we're going to go about this. We have this little nugget right here, which is super important, because what that tells me is I can write v1 as 1/4, negative 1/4 v2. And again, I'm just doing algebraic manipulation on this equation. So trying to isolate the v1, let's just make this simpler. If I were trying to isolate v1, I would have 4v1 equals negative v2 minus 3v3. And then, of course, v1 would be negative 1/4 v2 minus 3/4 v3. So therefore, v1 could be written as a redundant vector because it can be written as a combination of the other vectors. I could do the same for v2. v2 would be a little bit easier. v2 is just negative 4v1 minus 3v3. And I could do the same thing for v3. So essentially what I'm saying is any of these could be written as a redundant vector, and therefore one basis could be just using v1 and v2 by taking out v3. One basis could be v1 and v3 by taking out v2. And one basis could be v2 and v3 by taking out v1. And whichever one I take out doesn't really matter because the two that are left over are not linearly dependent. They are in fact linearly independent, which you can check very easily. And therefore, using that spanning set theorem, any of those could be a basis because I'm taking out the one redundant vector. One last example for us to look at together, we are looking at the basis for the column space of A. So A is this matrix made up of vectors A1 through A5. And as you can see, I already have it reduced to reduced row echelon form. And if I wanted to, I could point out that this is a pivot, and this is a pivot, and this is a pivot, and the other values are not pivot columns. What I'm looking for is a basis. So if we recall, a basis has vectors that are linearly independent, which means they cannot be written as linear combinations of one another, and they still span, in this case, the column space of A. So looking at these columns or vectors, this is vector A1, A2, A3, A4, and A5. A1 is it contains a pivot, and therefore I'm going to leave it just as it is. A2 can be written as just 5 times A1. So A2 is a redundant vector. I don't need it, is essentially what I'm saying. A3 is a pivot, so pivot, pivot. A4, however, is not a pivot column, so A4 can be written as -3 times A3, and then A5 does contain a pivot. So the spanning set theorem tells me that I can discard A2 and A4, and therefore the set of A1, A3, and A5 are still going to span the column space of B. And of course, that's my basis. And so if I wanted to, I could write this as those vectors instead. So 1, 0, 0, 0, 0. And A3 is 0, 1, 0, 0, 0. And A5 is 0, 0, 0, 0, 1. And in fact, we do have a theorem in your text, and you can look at the proof in your text, but we have a theorem that says the pivot columns of matrix A form a basis for the column space of A. So this was not a proof of that, but this was a really good example to show that in fact will be true. Anytime I can write any vectors as a linear combination of other vectors by the spanning set theorem, it tells us we can eliminate them, and what's left over will be linearly independent and therefore form a basis. Here's just one more practice for you to try. And notice on this question, I have not row reduced it for you. So your job is to first row reduce it, then find the basis for the column space of A. So press pause, try that question. When you're ready, press play to see how you did. So again, I'm going to start by just doing some row reduction. I'm trying to reduce this to reduced row echelon form. I'm going to take my second row times 1/4. And that's all I'm going to do on my first step. Typically I wouldn't do that first, but that's okay. That just came to me and I decided to go with it. So now I'm going to take -1 times my first row and add it to my second row. I'm sorry, my third row. I'm going to leave that second row exactly as he is. My third row, I'm going to take -1 times 1 and add it to 1. -1 times 3 to get -3 and add it to -2. -1 times -2 to get +2, add it to -2 to get 0. And I can see what's going to happen here. I've got 1, 3, -2. I've got 0, 1, 0. And if I take 5 times row 2 and add it to row 3, then I end up with 0, 0, 0. Now here's why I wanted to do this particular example. As you can see, I have 2 pivot columns. And what is important to understand is when I'm finding then my basis for the column space of A, I am going to write the original, so this is column 1 and column 2. My basis is the original column 1 and the original column 2. So I'm not going to write 1, 0, 0 and 3, 1, 0. I'm going to write 1, 0, 1 and 3, 4, -2, and that is my basis for the column space of A.